Welcome to a short screencast on Unit 8, Liquids and Solids. This will cover the material that was not done during class the last couple of weeks. And the first question deals with carbon tetrachloride, CCl4. This used to be used for dry cleaning. It's a refrigerant, but it is a compound that contributes to the depletion of the ozone layer. It's a greenhouse gas, and it's toxic. It affects the liver. And for those reasons, it's now banned from being used for consumer goods. And this question gives us the temperature and vapor pressure of CCl4 at a particular point. It's enthalpy of vaporization, and we're asked to estimate the normal boiling point for CCl4 from this. Now, a quick note, when we're dealing with vapor pressure, which is dependent upon temperature, so there's a vapor pressure curve and pressure temperature data points along that. That curve is kind of exponentially shaped, and there's an equation for how pressure and temperature are related to each other, and in particular, that equation can be put into a form where it relates the temperature and pressure, vapor pressure at 2 points on the vapor pressure curve, and it turns out that's related to the enthalpy of vaporization. So this is the equation. It's called the Clausius-Clapeyron equation. I will in no way, shape, or form try to derive it here. This is just something that is a given, and the purpose here is to see when this equation applies and how to use it mathematically. So this equation is the natural log ln, log base e, of the ratio of pressure 2 over pressure 1, and that equals negative enthalpy of vaporization over the gas constant R, times the quantity 1 over temperature 2 minus 1 over temperature 1, and of course the temperatures have to be in Kelvin for this equation to be applicable. So this is an equation that if we know two pressure temperature points on the vapor pressure curve, we can find the delta H of vaporization, or if we know one of the pressure temperature points, the delta H of vaporization, and let's say either the temperature or the pressure of the second point, we can find that. In fact, if there of any of the 1, 2 pressures, 3, 4, 2 temperatures, and delta H of vaporization. So there's 5 different values in this problem that could vary from substance to, will vary from substance to substance. If we know any 4 of the 5, we can find the 5th. Okay, so let's see how we do this. So there's a little bit of interpretation that's involved here too. So here's the data given, and the first temperature, 57.8 degrees Celsius, of course needs to be converted to Kelvin, and that is its pressure. And so I'm just choosing to call this point 1, P1 and T1. And then we're trying to find the normal boiling point, so we want to find a temperature. And it's important to note that the temperature that corresponds to the normal boiling point, well, that's normal boiling point means that the vapor pressure equals atmospheric pressure, which is 1 atmosphere, or 101.3 kilopascals if we're in units of kilopascals. So the second pressure temperature point, we don't know the temperature. That's what we want, the normal boiling point. And the normal boiling point corresponds to a vapor pressure equal to atmospheric pressure equal to 1 atm if we're at sea level. So we want to find T2. We know P1, T1, P2, and we know delta H of vaporization. So in this equation, we know everything except for T2. So we plug in the values, and P2 is 101.3 kilopascals. P1 is 54 kilopascals. These have to be in the same units, so the units cancel. Delta H of vaporization, I converted to joules per mole because the R value we should use is the 8.314 joules per mole Kelvin. So either R needs to be changed to kilojoules, or the delta H needs to be changed to joules. I chose the latter, And so now the joules will cancel and the moles will cancel and the units of kelvins will survive. And that's going to end up canceling out with the kelvins here. And then 331.0 Kelvin is T1 and T2 is not known. So we're going to solve this for T2. So we just do some math and we get an answer for T2 in Kelvin, 350.6 Kelvin. And we could just report the value in Kelvin, or if you're asked for it in degrees Celsius, you can do the usual 273.2 degree shift to get to the degree Celsius temperature, 77.4. Okay, now some of you, maybe many of you, can do the math on this just fine and would get this, but let's go through the mathematical steps just in case some of you are a little less familiar with in particular logarithms and just how to deal with this. And the big thing is math solving for an unknown. As always, you want to get it by itself. You isolate the unknown or the variable. So here's the equation all set up. And again, we're making sure pressures are in the same units. The delta H and the R are in the same units. And then the temperature has to be in Kelvin. And usually, probably the easiest thing to do is just to actually take the ln of this quantity and see what it is. Make sure this is in parentheses, and make sure you use the natural log ln button on your calculator. This is log base e. Do not use log, that's log base 10. So you'll take the ratio of 101.3 over 54. See what that is, and then take the ln of that. That's 0.6291. And then this fraction here, 32,500 divided by 8.314. I divided that out, and it's 3,909. And then, of course, there's the negative sign. And then I also divided 1 by 331, and that's 0.003021. Be a little careful with sig figs. I'm just carrying at least 4 sig figs throughout to make sure we don't have any errors due to rounding off too much at intermediate steps. And now again, we're trying to get T2 by itself. So you're going to want to divide both sides by negative 3,909 to get rid of that. And 0.6291 divided by negative 3,909 is negative 1.6909 times 10 to the minus 4th. And then that is equal to this stuff here, 1 over T2 minus 0.003021. And then you're going to want to get rid of the 0.003021. So add that to both sides. And adding 0.003021 to negative 1.690409 times 10 to the minus 4th is 0.002852. And then that equals 1 over T2. And then you can set this up as 2 fractions and cross multiply. I tend to like to just flip the whole thing over. So this part here, I'm going to flip over the 0.002852 and flip over the 1 over T2. So that gives us T2 equals 1 over 0.002852. And then dividing that out gives us 350.6. And we'll now remember the units are Kelvin. I left out the units as we just worked through the numbers. So once we're in the right units, we can kind of leave those off as we're just doing the math. And then, of course, subtract 273.2, and we get 77.4 degrees Celsius. Okay, next one deals with no calculations. This deals with intermolecular forces, and specifically hydrogen bonding, which is very important in DNA. And you may know from a previous biology class that DNA has 2 strands, and those strands are held together across pairs of nucleotide bases. Thymine and adenine is one of the pairs of nucleotide bases, and cytosine and guanine is the other pair. And these always pair up in that way. Thymine always pairs up with adenine and cytosine with guanine. And the reason has to do with the locations of the hydrogen bonds between these pairs. And so on the image here, I have thymine and adenine arranged in the right orientation for being able that they actually hydrogen bond, and same with cytosine and guanine. And so please pause the video and see if you can draw in the locations of all hydrogen bonds between thymine and adenine, and then cytosine and guanine. And it'd be really good if you try to do that, pause the video, and then we'll go over it. Okay, so I hope you paused. I hope you made an attempt. And thymine has hydrogen bonds in these two locations. And let's explain this just a little bit. So in the adenine, here we have an NH. That is the necessary condition, or meets the necessary condition for hydrogen bonding. We have nitrogen bonded to hydrogen in one molecule. That makes the nitrogen slightly negatively charged, the hydrogen slightly positively charged, and that's a very strong dipole. And the slightly positive charge on the hydrogen in adenine is then attracted to the slightly negative charge of this oxygen in thymine. Now notice, in thymine, if it was just thymine, this doesn't have the right conditions for hydrogen bonding, because although there's an oxygen, it is not directly bonded to a hydrogen. But adenine does, and so if one of the two molecules has N bonded to H, or O to H, or F to H, and the other molecule has an O or an N or an F not bonded to H, that's enough for hydrogen bonding. One of the two molecules has to have N to H, or O to H, or F to H, and the other one has to have that just the N or the O or the F. So thymine, same thing for this second hydrogen bond, N to H, that's what's needed for hydrogen bonding. N on the adenine opposite it, so the slightly positively charged hydrogen here attracts the slightly negatively charged nitrogen there, and that's a hydrogen bond. And there are two hydrogen bonds in the thymine-adenine pair. If you didn't already, try this for cytosine and guanine, or if you're rethinking it based upon the answer for thymine and adenine, please pause the video and give it a try. See if you can think of where the hydrogen bonds would be for this. And then we'll do it. There's 1, there's 2, there's 3. And it's the same basic idea as we had for thymine and adenine. NH, needed for hydrogen bonding, attracts the oxygen opposite it on the guanine. So the NH in the cytosine, that's what makes the hydrogen bond possible. The hydrogen attracts the oxygen in guanine. The second one, NH in guanine, that's what's needed for hydrogen bonding, and then the H in guanine attracts the nitrogen opposite it in cytosine. And then here's another NH in guanine, and the hydrogen in that is in the right location to attract the oxygen in cytosine. And so notice, cytosine guanine has 1, 2, 3 hydrogen bonds. Thymine and adenine has 2. And that is the reason why thymine and adenine always pair up, cytosine and guanine always pair up, because they have the right structures to complement each other, is the way it's often stated. Here's zooming out a little bit what the picture looks like. So here's thymine to adenine and the 2 hydrogen bonds. Here's guanine and cytosine, 3 hydrogen bonds. And then remember that these nucleotide bases are attached to a sugar phosphate backbone. So here's the sugar, there's the phosphate, here's the sugar, there'd be another phosphate here, here's the phosphate, there'd be another sugar there, another pair of bases, and then same thing on the other strand. The cytosine attaches to a sugar, which is attached to a phosphate. The adenine attaches to a sugar, which is attached to a phosphate, and then this sugar-phosphate backbone or chain is one of the strands of the double helix, and then this continues. And so now we zoom out a little bit more, and we can see an adenine-thymine pairing as one maybe rung of this ladder, then a cytosine-guanine pairing, then an adenine-thymine, and then whatever the order of these is, that determines the information in DNA. And then we have these double helices wrapping around each other, and this can zip and unzip, so to speak, relatively easily without destroying the structure of the DNA, because the hydrogen bond, there's so many of them, and they're so strong as intermolecular forces that it holds the DNA together fairly well, but they're not so strong that they can't be overcome in the process of replication, and that's much easier to do to overcome even a whole bunch of hydrogen bonds than to break bonds, which ends up destroying the structure and the function. Okay, and the very last one, we have 3 isomers of C5H12 that we're going to order from lowest to highest boiling point with an explanation. And first of all, what do we mean by isomers of C5H12? Well, if we have 5 carbons, an appropriate number of hydrogens, one thing that could happen is all 5 hydrogens could be kind of just in a row. So carbon bonds to carbon, bonds to carbon, bonds to carbon, bonds to carbon, 5 of them bonded with the appropriate number of hydrogens. This is often called a straight chain, even though it's actually kind of bent, but the carbons bond one to the next to the next. So it's like it's a chain, even though it's not technically really straight. And we often call this N-pentane for normal pentane. Now we can also have 4 carbons in a chain, 1, 2, 3, 4 carbons bonded to each other, and then the 5th carbon branches off of that 4-carbon chain. Now a 4-carbon chain with all single bonds and appropriate numbers of hydrogens is called butane, and then a 1-carbon group is called methyl, and it is branching off of the 2nd carbon, so the systematic name for this is 2-methyl-butane, because the main chain is butane. There's a methyl group branching off of carbon number 2. And then this also has a common name, which is isopentane, and either one of these can be used. The systematic name is very useful for naming complicated things because there's just like one way you can do that. The common names, they aren't systematic, and so you simply have to depend on memory. You can't figure them out. So often we use the systematic names, but here I'm going to use the common ones just because there's only 3 isomers to deal with. Okay, well, there's a third. The third isomer is 3 carbons in the main chain, 1, 2, 3, and then the 2 other carbons branch off from the middle carbon, and 1 carbon branches off here, sort of shown to the top, and the other carbon branches off, shown here to the bottom of that main chain. And so we have a 3-carbon long chain, which is called propane, and then a methyl group and a 2nd methyl group branching off of the 2nd carbon. So there are 2 methyl groups, so we say dimethyl, and they both branch off of the 2nd carbon, so we put 2's in front. So the systematic name is 2,2 dimethyl propane. Propane's the main chain, a methyl group, there's one of them, and a methyl group, there's a second one, so dimethyl, and this methyl group branches off of carbon number 2, and this methyl group branches off of carbon number 2. And then the common name for this is neopentane, so we're going to just use that from now on. N-pentane, isopentane, and neopentane are the 3 isomers. And quick note, they all have the same molar mass. So in some sense, their size is the same, but their structure isn't. And that actually is quite important, and these 3 isomers have different boiling points, so you might want to try to predict which one has the highest and which one has the lowest and what your reasons are. And pause the video, and then we'll go over the answer. And it turns out that neopentane has the lowest boiling point, N-pentane has the highest, with isopentane in the middle. And let's take a look at the reasons why. And here we have to kind of look at the structures and specifically the shapes. So this one's neopentane. We have a space-filling molecule of this, and here's a neopentane attracting a neopentane, and you can see the surface area of contact, which is where these intermolecular forces of attraction are going to be, and these are all nonpolar molecules, so these are all going to be just dispersion forces. They're pretty much when 2 molecules get close together, 2 neopentane molecules, this is the region where they can attract each other. Now, isopentane is not as compact as neopentane. It's 4-carbon chain with a branch rather than a 3-carbon chain with 2 branches, and it has a larger surface area than neopentane. And then we'll continue on to N-pentane, which is a quote-unquote straight chain, 5 carbons in a row, and these can attract each other over this amount of surface area when they're in this arrangement. So N-pentane has the largest contact area, the strongest dispersion forces attraction, because it really has to do with the attractions between two molecules, not really just their mass, but how much the electron shells can attract each other for dispersion forces. So this has the strongest attraction because of the largest, we say, contact area, because this is the least compact molecule, so that has the highest boiling point. Neopentane has the smallest contact area and the weakest attraction, the weakest dispersion forces, because it's the most compact molecule, so it has the lowest boiling point. And then isopentane has the intermediate surface area, intermediate attraction, and intermediate boiling point. Now, of course, this applied because these 3 compounds all have the same mass, so they're nominally equal in that sense, and then we have to look more at the structure. But in general, we really do have to look at the structure perhaps just as much as the mass of the molecules in order to be able to determine and make predictions about properties that are dependent upon intermolecular forces, such as boiling point. Okay, and that is it for the material we did not cover in Unit 8, Liquids and Solids.